Hello, welcome to the last in our series of Power Base. In today's programme, we're going to be introducing you to two vitally important components in many electrical circuits, the capacitor and the inductor.
And we'll see how a capacitor stores up the electrons to make this flash gun flash.
And how a simple coil of wire called an inductor can make electrons very stubborn. But first, let's have a quick look at what we learnt last week. When an electron moves, it creates a magnetic field around itself like a bow wave. If the electron isn't moving, there's no magnetism. The magnetism of a single wire is quite weak, but we can concentrate it by forming the wire into a coil. Transformers only work with alternating electric current, which generates an alternating magnetic field, which in turn induces another alternating electric current in the other coil. Electrical engineer Fenella Hume is with us as usual. Fenella, throughout the series we've used the television set, thank you very much, to point out circuits and components as we've been looking at them. Remind us of some of the things that we should now be familiar with.
Well, one of the most obvious things, the power into the television comes in through this insulated cable here. Colour-coded, you remember? Live is brown, green-yellow is earth, and blue is neutral. You'll notice from this, actually, that
There's the earth.
Earth
bolted onto
is bolted onto the chassis. You remember we said that was very safe.
What else?
Another thing we've seen before, transformer here. This one's actually a step-down transformer. There's another one over here, which is a step-up transformer that provides a very high voltage into the tube.
And how about the components we're interested in today, capacitors, for instance?
We'll be looking at a capacitor. There's a lovely big black cylinder here, and that is a capacitor.
Now, when we first looked at a set like this, you were emphatic you should never do this. Why is looking into the back of a television set dangerous?
Well, two things mainly. The first is obvious. We've got safety goggles on in case that glass tube actually shatters. The second thing is capacitors, and that's what we'll be looking at today, have the ability to store electricity. So even with the set switched off and unplugged from the wall, if you put your finger on a capacitor, you might well get a nasty shock.
So is that their value, this ability to store charge?
Not only that, the other thing that they do as a component controlling electricity is isolate AC from DC. What they do is let AC current pass through, but block all DC.
We have a larger version of the Open College course kit in the studio, and on this I can demonstrate some of the characteristics of a capacitor. Now, if I try to light a bulb using AC, which is going through the capacitor, the bulb lights quite happily. Now, if I change from AC to DC by going through the AC to DC converter, then if I connect the bulb through the capacitor again, using direct current, you can see that no electricity gets through and the bulb remains off. So, a capacitor passes AC but blocks DC. But how do capacitors work? Well, all these capacitors work in exactly the same way. And on this variable capacitor, one of the connections up here leads to this set of metal vanes, which moves around. The other lead is connected to this fixed set of vanes. Now, the two sets of vanes are separated by air, which, as you remember from earlier programs, is an insulator. Now, here is another capacitor which has already been partly dismantled. Now, when it's unravelled, you can see that it's actually two pieces of metal foil separated by an insulating material. Now, imagine that this is a capacitor. This side is one plate of it, and this side represents the other plate. Now, when a voltage is applied across the capacitor, electrons flow in from one side and fill up one of the plates. The electrons on the other plate are forced out down the wire. Now, once the capacitor has been filled up with charge, everything comes to a standstill. This insulating material won't allow any current to flow between the plates. And that's why a capacitor has infinite resistance to direct current. On the other hand, with AC, the voltage continually changes. When the current is flowing one way, one side fills up. When the current changes, the other side fills up. So in this way, the charging and discharging allows current to flow back and forth. The capacitor, therefore, has only a small impedance to AC. And if you haven't come across the word impedance before, don't worry. It's very similar to resistance, only it's more technically correct to say impedance when you're dealing with alternating current. Now, let's have a look at all of that again with our animation.
A capacitor, as we've seen, is just two plates of metal separated by an insulator. When a voltage is applied, electrons are pushed into one side of the capacitor and pulled out of the other side. When one side is full and the other is empty, the capacitor is charged. If the voltage then changes, the electrons will flow back round the circuit and even out the balance. With DC, a current flows while the capacitor is charging up, but is then blocked completely. With AC, the capacitor charges, then discharges continuously, so there's very little resistance to the flow of electrons. The ability of a capacitor to block DC but to allow AC through is very useful, especially, of course, in applications where we only want to use an alternating current. And since the capacitor can store charges, it will still supply a current to circuit even after the power has been turned off. You'll notice on some radios and amplifiers how the sound takes some time to fade away after you've turned the power off. That's capacitors at work. Capacitance, the ability of a capacitor to store charge, is measured in a unit named after our old friend Michael Faraday. You'll remember him from last week's program. He invented the electric motor. The unit of capacitance is the farad. Now, the capacity of a capacitor depends on several things. The larger the area of metal plates, the larger the capacity. Also, the thinner the insulation between the plates, the larger the capacity. And finally, the material of the insulator. Plastic, ceramic, paper, and air are all used in capacitors. But using certain insulators, we produce capacitors which can only be connected one way round. These are called electrolytic capacitors, and if you do connect them the wrong way round, well, this is the sort of thing that can happen. We went to ERA Technology in Leatherhead to see power storage capacitors being manufactured and tested.
As we've seen, capacitors are made up of two sheets of metal separated by an insulator. To build up a large capacitance, we need a large surface area of metal, and the easiest way to package this is by winding together strips of metal foil. Once the capacitor is big enough, foil electrodes are added so that the capacitor can be connected to a power supply. On this machine you can see that there are two reels of metal foil being wound together, separated by the thin plastic film. Its ability to store charge can now be tested. First of all, the capacitor is connected to a power supply which pushes electrons onto one plate and off the other. The fuller the capacitor gets, the higher the voltage across its terminals. At around 300 volts, the capacitor is disconnected from the power supply and connected to a neon bulb. The accumulated charge redistributes itself evenly between the two plates by going through the neon bulb, discharging the capacitor. This type of capacitor is usually put together with a large number of others into a stack like this. When all this capacitance gets together, the amount of charge stored is very great. If we charge it up to around 10,000 volts, eventually there's enough pressure in the system for the electrons to jump the air gap, discharging the capacitor in a miniature flash of lightning.
Fenella, clearly capacitors are very versatile bits of equipment, but what do they actually do? What is the purpose they serve in the television set, for instance?
Well, because of their ability to actually let AC through and stop DC coming through. You can imagine that they're very good as filters. They say, yes, please, AC through, no thanks to the DC. And so they can be good for controlling what type of current actually gets into which bits of the circuit.
I know, too, that capacitors have other roles, and no doubt they're going to crop up as we develop our study of electronics. So anyone who's going to stay with that will find capacitors old friends by the time we get to the end. But does a capacitor inside this flash gun play exactly the same role?
No, it doesn't. Inside this flash gun, it's actually charging up. It's filling up with electricity until it's got enough energy to actually jump across a gap in here so that you get a spark as the electricity crosses the gap. If you remember, we needed a lot of voltage for that, a high voltage, and we used the capacitor to charge up to that high voltage to give it enough energy.
And is that high energy discharge the same sort of application in this little device, which fits into a fluorescent tube, gets that going?
Yes, it is. You need, again, a lot of energy, a high voltage, all at once to actually get the gas in here burning to begin with. That's why sometimes you see a flicker, because it doesn't immediately have enough charge to do that.
Then as the capacitor charges up, so enough energy is created.
That's right.
Well, there we are. We've got an introduction to the capacitor. Let's move on to the other component we're going to talk about in this program, the inductor. Can you point one out in the television set?
Right. If we look over this side, there's a big round blue thing here that looks like it might be a coiled piece of wire in there, and that actually is an inductor, a coiled piece of wire.
So if an inductor is a coil, what purpose does it serve?
Well, it's complementary to the capacitor, really, because the inductor actually lets DC current pass through it, and it says no, it stops the AC.
In the same part of the kit which contains the capacitor, we also have an inductor. So let's do the same experiment we did with the light bulb, only this time we'll use the inductor instead of the capacitor. Now, I've connected the light bulb to an AC power source which goes through the inductor. And you can see that the bulb does light, but it's quite dim. It's not as bright as when I bypass the inductor and connect the bulb straight through to an AC power source. Now that means that there must be some resistance in the circuit which contains the inductor. Now here I should point out again that there are special words for the different ways in which an inductor reduces alternating current. For simplicity, we'll just say that the inductor is impeding the current. Now, I'll connect the bulb to a DC power source via the AC to DC converter. And we'll use the circuit containing the inductor again. Now the bulb shines just as brightly using DC through the inductor as when it's connected to AC bypassing the inductor. So, an inductor impedes AC but allows DC straight through. Well, why is that? In last week's programme we saw how moving electrons in one wire can affect the electrons in another wire. But how do they affect each other? Well, in an ordinary wire, the magnetic field produced is so weak that it doesn't really have any noticeable effect on the flow of electricity. However, if we concentrate the magnetism in the usual way by forming the wire into a coil, the effect of the current on itself does start to become noticeable. As the electrons go round, they create a magnetic field which encourages them to carry on going round. It's a bit like this bicycle. Now there's no freewheel mechanism on this, so once I start the wheel turning, it wants to carry on turning. And if you think of DC as a steady, continuous push in the same direction, then you can see that this arrangement will quite happily let DC through. Not only that, but it will also try and stop the level changing. If I try to speed up or to slow down, the wheel reacts against the change that I'm trying to make. So the inductor likes DC and tries to keep the current at the same level. But what about AC? Well, AC is constantly changing. So the pedals need to go first one way and then the other. And you can see that if I try and change the direction of the wheel quite slowly, I don't have too much of a problem. But the more quickly I try to alternate the direction the wheel turns, the harder it becomes. And that's exactly how an inductor reacts. The faster you try to alternate the current, the less current makes it through. In other words, the inductor doesn't like change. Ideally, it wants the direction and the level of the current to remain the same. In effect, it's making the electrons very stubborn. Whatever they're doing now, they want to keep on doing. They react against any change. In fact, the characteristic is called reactance. Now, let's look at all of that again with the help of our animation.
Remember that a moving electron creates a magnetic field, and that a moving magnetic field makes electrons move. So, when we put moving electrons together, they're encouraged by each other's magnetic fields. If we concentrate that magnetism by making the wire into a coil, forming an inductor, the electrons become stubborn. They want to carry on moving in the way they have been. They'll be slow to change. So an inductor lets DC through, but reacts against change. Fenella, is the inductor a particularly important component?
Yes, it is. It's a very valuable component. But on its own, it's not enough. We don't live in an ideal world, and in fact, none of these components are ideal. The capacitor isn't a perfect DC block, and we've shown that the inductor isn't a perfect AC block. So we use these two together to get what we want. If you look at this power supply here, it's called an uninterruptible power supply. And part of the circuitry in here provides a very pure DC, which it needs for its own use. The way it does that is by using capacitors to let the AC find a path away from the required circuit, and it uses inductors to let the DC through. And in that way, it uses the complementary characteristics of these two to make a much better circuit.
Remembering earlier in our series how many appliances seem to run on DC, it sounds as if capacitors and inductors are going to keep on cropping up in the world of electricity.
You'll see them almost everywhere in every piece of circuitry, both with electricity and electronics.
Fenella Hume, thank you very much, and thank you for all your help throughout PowerBase. Well, we've almost come to the end of this series, but before we say goodbye, let's take a whirlwind tour of these last 5 programs.
When tiny particles called electrons are persuaded to move through a material, an electric current flows. Such materials are called conductors. A current will only flow in a conductor and will only flow around a circuit. Current strength is measured in amps. The more electrons flowing, the stronger the current. The pressure that keeps the electrons moving is measured in volts. Batteries produce electron flow in one direction, and that's called direct current, whilst a generating station produces an electron flow first one way and then the other. It's called alternating current. Although many appliances use direct current, it's more convenient to transmit alternating current over long distances.
Electricity can be made to produce heat and light by forcing it through resistance. Something can have a high resistance either because of the metal it's made of or because of the conductor, which is stretched out until it's very thin. Resistors are used in electrical circuits to control voltages and currents. Resistance is measured in ohms. Resistors can be put together in 2 different ways: in series, where the total resistance is just the sum of all the resistors, or in parallel, where the total resistance is less than any one of the resistors. The relationship between voltage, current, and resistance is called Ohm's law and can be remembered with the VCR triangle. Power is measured in watts, and the relationship between power, voltage, and current can be remembered with the PVC triangle. The amount of electricity we use in the home is measured by the electricity board in units called kilowatt hours. To find out how much electricity something has used, we multiply its power by the amount of time it has been switched on.
Electrical equipment and current-carrying cables are segregated from people using distance, fences and warning signs. All current-carrying conductors should be insulated. The insulation carries a colour code which must be strictly observed at all times. Any switches must be inserted in the live wire in preference to the neutral wire. Fuses and circuit breakers are safety devices which open the circuit when too large a current flows. The fault which caused the circuit breaker or fuse to open the circuit must always be found before the circuit breaker is reset or the fuse is replaced. All metal parts of an appliance not in the circuit must be earthed.
When an electron moves, it creates a magnetic field around itself like a bow wave. If the electron isn't moving, there's no magnetism. The magnetism of a single wire is quite weak, but we can concentrate it by forming the wire into a coil. Such a coil is called an electromagnet and allows us to form a magnet at the flick of a switch. One of the many uses of an electromagnet is in a relay, which allows one small current to control several others. Magnetism, electricity, and movement form a trio. Putting any of the two together, we produce the third. A motor uses electricity and magnetism to produce movement. A generator uses movement and magnetism to produce electricity. Transformers only work with alternating electric current, which generates an alternating magnetic field, which in turn induces another alternating electric current in the other coil. The input and output voltages of a transformer are in the same proportion as the number of turns on the primary and secondary coil. If there are more turns on the secondary than on the primary, it's a step-up transformer and produces higher voltages to make sparks in car engines and drive electricity long distances in power lines. If there are fewer turns on the secondary than on the primary, it's a step-down transformer and produces lower voltages. These are found in most pieces of electrical equipment, stepping down from mains voltage to lower voltages used in electronics.
Capacitors are electrical components that can store an electric charge. They have an infinite resistance to direct current, but only a small impedance to alternating current. Capacitors take some time to charge up and to discharge as well. The higher the capacitance, which is measured in farads, the more electrons are stored and the longer the capacitor takes to charge up. Inductors are wire coils that use electromagnetism to keep the current flow steady. They have a low resistance to DC, but react against any change. If the current flow increases, they will resist the excess current. On the other hand, if the current decreases, they will aid the current flow.
And there you are, 5 programs in 5 minutes. And you can follow up this program, indeed the whole series, at your own pace with the Open College course on basic electricity. And for details, write to Power Base, the Open College, P.O. Box 35, Abingdon, OX143BR. Goodbye.
Bye-bye.
College on 4. Now the secrets of electronics will be unveiled in circuit training.
Hello, welcome to Circuit Training, a series of programs designed to help those of us who believe we're not technically minded come to terms with electronics. One way or another, electronics have entered nearly every area of our daily lives.
For instance, most of us have quite a few pieces of electronic equipment in our homes. Televisions, video cassette recorders, microwave ovens, washing machines, and even toasters and kettles now contain electronics. And in offices, factories and shops, in warehouses and hospitals, and in almost every sort of workplace, the range of electronic equipment used is almost endless.
I'm Michael Rodd, and in these programs, Carol Vorderman and I will be providing a background designed to help anyone to get the most out of the Open College course on basic electronics. A training package designed for you to do on your own to provide a comprehensive layman's introduction to this subject.
Part of that pack, and we'll be telling you how to get hold of one a little later in the programme, is a kit which allows you to do all sorts of experiments and tests perfectly safely at home. In the studio, we've built a larger version of this same kit, and I'll be using this throughout the programmes to bring alive the concepts that we'll be talking about.
By following our programme and the Open College course, you'll be able to see for yourself what electronics is and how a simple understanding of the building blocks that make up electronic circuits can help you to play a more active role in electronics, perhaps by getting into one of the growing number of businesses and industries involved in this technology of today. But don't take our word for it. Listen to what some of the people already involved in electronics have to say.
Even people who know very little about electricity can learn very rapidly about the function of electronic devices and electronic components.
I'm an electrician by trade, and I look on electronics as a natural progression for me.
I would like to go forward to learning more in electronics, to going on to testing in electronics. I would like to do that.
It is undoubtedly an advantage if people come to us with some prior knowledge of electricity, electronics.
We always encourage people to take outside courses because the nature of the game in electronics is that it is a very rapidly advancing technology. It's always changing.
Training is very important for this type of work. When the girls first start, usually they don't know nothing about electronics or electricity. And first of all, we sit them down and just learn the basics, and then they take it from there, and gradually they learn more each day.
A familiar face to those of you who've been following Powerbase, electrical engineer Fenella Hume is with us again to shed a bit of expert light on this subject. Fenella, I'm sure many people will find the prospect of electronics a little daunting. Are there some simple ground rules to make it easier?
Well, the one thing that you should remember is that all electronic circuits are made up of very basic building blocks, all put together. What we're going to do here is actually show you how simple these building blocks are, and then no electronic circuit, however complex, will be that daunting.
Throughout this series, as with the Open College course it accompanies, we'll be assuming that you have no prior knowledge whatsoever. However, it will be useful if you understand some of the basic ideas about electricity, the sort of thing we covered in our previous series, Powerbase. So, before we ask the question, what is electronics, let's quickly answer the question, what is electricity? When tiny particles called electrons are persuaded to move through a material, an electric current flows. Such materials are called conductors. A current will only flow in a conductor and will only flow around a circuit. Current strength is measured in amps. The more electrons flowing, the stronger the current. The pressure that keeps the electrons moving is measured in volts. Batteries produce electron flow in one direction, and that's called direct current, whilst a generating station produces an electron flow first one way and then the other. It's called alternating current. Although many appliances use direct current, it's more convenient to transmit alternating current over long distances.
Electricity can be made to produce heat and light by forcing it through resistance. Something can have a high resistance either because of the metal it's made of or because of the conductor, which is stretched out until it's very thin. Resistors are used in electrical circuits to control voltages and currents. Resistance is measured in ohms. Resistors can be put together in two different ways: in series, where the total resistance is just the sum of all the resistors, or in parallel, where the total resistance is less than any one of the resistors. The relationship between voltage, current, and resistance is called Ohm's law and can be remembered with the VCR triangle. Power is measured in watts, and the relationship between power, voltage, and current can be remembered with the PVC triangle. The amount of electricity we use in the home is measured by the electricity board in units called kilowatt hours. To find out how much electricity something has used, we multiply its power by the amount of time it has been switched on.
Electrical equipment and current-carrying cables are segregated from people using distance, fences and warning signs. All current-carrying conductors should be insulated. The insulation carries a colour code which must be strictly observed at all times. Any switches must be inserted in the live wire in preference to the neutral wire. Fuses and circuit breakers are safety devices which open the circuit when too large a current flows. The fault which caused the circuit breaker or fuse to open the circuit must always be found before the circuit breaker is reset or the fuse is replaced. All metal parts of an appliance not in the circuit must be earthed.
When an electron moves, it creates a magnetic field around itself like a bow wave. If the electron isn't moving, there's no magnetism. The magnetism of a single wire is quite weak, but we can concentrate it by forming the wire into a coil. Such a coil is called an electromagnet and allows us to form a magnet at the flick of a switch. One of the many uses of an electromagnet is in a relay, which allows one small current to control several others. Magnetism, electricity, and movement form a trio. Putting any of the two together, we produce the third. A motor uses electricity and magnetism to produce movement. A generator uses movement and magnetism to produce electricity. Transformers only work with alternating electric current, which generates an alternating magnetic field, which in turn induces another alternating electric current in the other coil. The input and output voltages of a transformer are in the same proportion as the number of turns on the primary and secondary coil. If there are more turns on the secondary than on the primary, it's a step-up transformer and produces higher voltages to make sparks in car engines and drive electricity long distances in power lines. If there are fewer turns on the secondary than on the primary, it's a step-down transformer and produces lower voltages. These are found in most pieces of electrical equipment, stepping down from mains voltage to lower voltages used in electronics.
Capacitors are electrical components that can store an electric charge. They have an infinite resistance to direct current, but only a small impedance to alternating current. Capacitors take some time to charge up and to discharge as well. The higher the capacitance, which is measured in farads, the more electrons are stored and the longer the capacitor takes to charge up. Inductors are wire coils that use electromagnetism to keep the current flow steady. They have a low resistance to DC, but react against any change. If the current flow increases, they will resist the excess current. On the other hand, if the current decreases, they will aid the current flow. So that's electricity, but what is electronics? Why is a television electronic, whereas an electric fire isn't? Well, electronic equipment deals with very small voltages and currents, which are completely separate from the electricity that powers them. These small voltages and currents are called signals, and in a television, the signal is the program that's sent out from the transmitter and received by the television aerial. In an electric fire, there are no signals. The electricity just comes in and heats up the element. The signals that come into a television aerial have to be changed quite a lot to turn them into a TV picture and sound. And the circuitry that does this, when taken as a whole, is very complicated. But all circuits are made up of the same basic building blocks, just put together in different ways. Some of the building blocks you may already be familiar with. Resistors, capacitors, transformers and inductors we discussed in Power Base. Other components, like the diode and the transistor, we'll be explaining in this series, Circuit Training.
Here at Siemens, Europe's largest electronic manufacturer, electronic components are put together into circuits using high-speed robots. But not everything can be automated. There are certain parts of the process which still need the human hand and the human eye. When all the components are in position, the whole circuit board is passed over a wave of liquid solder, a molten metal which immediately sets, fixing the components in position and ensuring their electrical contact with the circuit printed on the board. As electronics is involved with very small voltages and currents, signals, two of the most important parts of any piece of electronic equipment are the power supply and the amplifier. Electronic circuits run on low voltage, direct current, and of course this can be supplied by batteries. But often it's more practical to use a power supply that's connected to the mains. As for amplifiers, their job is to magnify the tiny signals, the very small voltages and currents, to make them large enough to drive printers, turn motors, or do whatever the job is they have to do. But first of all, let's think about the power supply. Fenella, why is the power supply so fundamentally important?
Well, they provide the voltage to every component in the circuit. And you can imagine if the voltage on the component is too high, then it could get damaged. On the other hand, if it's too low, it probably won't work properly at all. So what we need is a voltage at just the right level. The other thing is it mustn't vary. So what you want is something that's what we call smooth. If it varies, the components get confused between that voltage and the voltage coming in controlling the component. So that's why a power supply is so important.
As we said earlier, if you join the Open College course on basic electronics, you'll receive a kit like this. We've got a larger version, which we'll be demonstrating on in the studio. Now, if you followed Powerbase, you may recognise this extra piece of equipment, and it's called an oscilloscope. Now, it's used by electronic engineers to show voltages with this dot which goes across the screen. Now, the kit is divided into three main sections, and we're going to look at the power supply section, that's the one at the top, first of all. Now, the first part of the power supply isn't on the board. It's this little black box, which is a transformer. And this converts the 240 volts AC coming out of the main socket into around 9 volts AC at this plug on the side. Now, at the moment, the oscilloscope is connected to the output of the transformer, and that's 9 volts AC. Now, you can tell it's AC because the voltage is going up and down across the centre line. And the important thing to remember is that this is alternating current because the voltage is first of all pushing it one way below the line and then coming back up in the other direction. So that's the first stage of the power supply, a transformer reducing the AC voltage. The next step in the power supply section is called the rectifier, and that's here. Now, this takes the low AC voltage from the transformer and turns it into a DC voltage. And I'll reconnect the oscilloscope to the output of our rectifier section. And we'll see that instead of the electricity going up and then down, it's now going in the same direction all the time. However, the output of the rectifier isn't a smooth DC voltage like you get from a battery. Instead, it's a series of positive voltage pulses. The rectifier has taken the negative part of the cycle, that's everything below the centre line, and flipped it over so that now the whole cycle is positive. So we have a series of positive pulses, a bit like a side view of the Himalayas. Now, to get a steady DC voltage, the pulses from the rectifier must first go through a smoothing circuit. And this is the third section of the power supply. So reconnecting the oscilloscope to the output from the smoothing section, you can see that what it's doing is smoothing out those bumps. Now, this gives a smoother but still not perfect DC voltage. The last section of the power supply is the stabilizer. Now, this irons out the wrinkles in the DC waveform, and reconnecting the oscilloscope once again, you can see that it keeps the voltage at a steady value. The voltage is now smooth and steady enough to be used by the other electronic circuitry in the equipment. So, these then are the four main parts of the typical power supply. First of all, we have the transformer, then the rectifier, the smoother, and finally the stabilizer. And we'll be going through all four of these in more detail later on in the series.
You're probably more familiar with the term amplifier when talking about hi-fis, so we've got a system here in the studio. It's the usual stacking sort with the turntable at the top and the amplifier section down here. Now, the job of the amplifier is to magnify the signal from the stylus on the record deck about 8,000 times so that we can hear it. Now, why is that? Well, if I turn the turntable on, and indeed you can do this experiment at home with your own record player, lower the stylus into the groove with the amplifier switched off. Listen. You can hear tinny sounds coming from the needle. In fact, a good quality record deck will give a signal of about 2.5 millivolts. That's 2.5 thousandths of a volt. But stereo speakers for this system need around 20 volts to enable us to hear all the sounds on the record. So the amplifier has to raise that 2.5 millivolt signal up to 20 volts, magnifying the signal from the record deck 8,000 times. And that's what happens when you switch in the amplifier. Televisions too have amplifiers, not just to magnify the sound signal for the speaker, but also to boost the invisible signals coming through the air so that the television can present them as pictures on the screen. But amplifiers aren't simply used to make audio or video stronger. All of these electronic devices use amplifiers. These electronic weighing scales have got sensing devices that produce tiny signals representing the weight of the produce. These are fed to a built-in computer, which then works out the price of the goods being bought. And all of the signals have got to be amplified to drive the display and to produce the printout recording the transaction. In offices, the tiny signals used in computers and word processors are amplified so that they can drive printers or put up displays on the screen. And wherever robots are used, the control signals, usually produced by a computer, must be amplified to drive the motors that control the position of the robot arm.
Here at Austin Rover, quite a lot of the manufacturing process has been fully automated. As we've said, two of the most important stages of automation are getting a steady, stable power supply and amplifying the control signals that the circuitry produces in order to drive robots, welding machines and lasers. The control circuits telling these robots what to do have to have absolutely rock-steady power supplies. If there's just a slight variation in that supply, then a weld might be put in at the wrong place. Then, further on down the line, the body goes into the laser inspection area. Here, the lasers, those little spots of red light, check that the body is exactly the right shape. If it isn't, it will be rejected. You may recognise these pieces of equipment from Powerbase. They're both transformers and they're the first part of our power supply section. Now, to refresh your memory, let's go over things again.
If an electron is standing still in a wire in a steady, unchanging magnetic field, the electron has no desire to move. If, however, the magnetic field moves or changes in some other way, the electron is forced to move and so create electricity. So magnetism moving or changing creates electricity. A steady, unchanging direct current creates a steady, unchanging magnetic field. And remember, a steady field doesn't make the electron want to move. On the other hand, an alternating current produces a constantly changing magnetic field, which makes the electron move. So if we feed an alternating current into one wire, then a similar current will be forced to flow in a nearby wire. This is what happens in a transformer.
Now, if we have, say, 200 turns on the coil that we're putting the current into, which is called the primary coil or the winding, and 200 turns on the secondary coil, then we get the same voltage out as we put in. But if we have, say, 100 turns on the secondary, then we get half the voltage out. That is, the voltages are in the same proportion as the number of turns. And we can see this relationship with another transformer which has a very, very large number of coils on the secondary. So what we'll produce is a very high voltage on this side. Now, a high voltage means the electricity can jump gaps. So when I close the switch, there's enough pressure in the system, enough voltage to make it jump from this line to this line and cause a nice climbing spark. And this is exactly the way they used to do it in the old horror movies, just before the villagers burned down the castle. Now, if I take the secondary winding off and replace it with this much smaller one, which you can see has a much smaller number of turns, then what we'll get is a very low voltage, but we'll have the ability to provide a very high current. So we need very good conductors to stop this secondary winding from melting itself. And if I put the weak link in, a nail, when I switch the power on, the very high current which flows melts the nail.
Fenella, let's quickly complete our understanding of transformers. The first sort that increase the voltage, they're used where?
They're used all over the country where we need that very high voltage to give the pressure to transmit electricity around the country. We use what's called the step-up transformer, which makes that very, very high voltage. Another very common place is in the car. Where you have the spark plug, you need a very high voltage to get the electricity to spark across the gap to start your car.
As we've just been seeing.
Yes.
And the other sort, the sort that reduce the voltage?
Well, those are very common as well, because if we look in this transistor radio here, and many other household appliances, have what's known as a step-down transformer, which takes the 240 mains from your supply, steps it down to a much lower voltage, which is then used to provide power to the rest of the circuit.
Fenella, thank you very much. Well, I'm afraid our time is up, but I hope that we've convinced you over the last 25 minutes or so that electronics is something that you can understand. We hope you'll follow circuit training over the next 4 weeks, and of course, we hope too that you're going to follow up on the Open College course on basic electronics. Now, for details of that, write to Circuit Training, the Open College, P.O. Box 35, Abingdon, OX143BR.
The training package, like these programs, starts from the assumption that you have only a basic understanding of electricity and takes you through the basics of electronics, explaining what it is and how it works.
Join us again next time on Circuit Training and we'll continue our television background to electronics. But let's leave you with a final reminder of what we've covered today.
Electronics is to do with the handling of very small voltages and currents called signals. The signals used by electronic equipment need to be boosted to provide a useful output. To do this, we use amplifier circuits. Most electronic circuits run on low voltage DC power, and the voltage must be kept smooth and stable to prevent distortion of the signal or damage to the components. This voltage can be supplied by batteries or by the equipment's power supply.
A power supply comprises 4 basic sections. The transformer, which changes mains voltage AC to low voltage AC. The rectifier, which changes the AC to DC. The smoother, which evens out the bumps. And the stabilizer, which further refines the supply.
The input voltage of a transformer is applied to the primary coil, and the output voltage is produced by the secondary coil. The input and output voltages are in the same proportion as the number of turns on the primary and secondary coils. If the secondary has more turns than the primary, then the output voltage will be higher than the input voltage. If the secondary has fewer turns than the primary, then the output voltage will be lower than the input voltage.
And that's it. Good luck with your own work, and until next time on Circuit Training, from all of us, goodbye.
Meaning.
Hello, welcome to the third in our series, Circuit Training. In this program, we're going to be seeing how we can iron out the bumps in the rough DC voltage we produced last week.
I'll be taking you through the next two stages of the power supply section on your kit.
And we'll be seeing how they produce power supplies which work even when the mains is cut off. But first, in case you're a newcomer to circuit training, what is it?
Well, it's a series of programs designed to help those of us who believe we're not technically minded come to terms with electronics.
In these programs, we're providing a background designed to help anyone get the most out of the Open College course on basic electronics. A training package designed for you to do on your own.
Part of the package, and we'll be telling you how to get hold of one a little later, is a kit like this, which allows you to do all sorts of experiments perfectly safely at home. And here in the studio we have a larger version of exactly the same kit, and I'll be using this to bring alive some of the concepts that we'll be going through.
By following our programs and by getting into the Open College course, you'll be able to see for yourself just what electronics is and how a basic understanding of its building blocks can give you an insight into the workings of any piece of electronic equipment. But first, let's see what we've learnt so far.
In the first program, we learned that electronics is concerned with handling tiny voltages and currents called signals. Because signals are so small, we need to use amplifiers to magnify them into useful working voltages. Also, it's very important for electronic equipment to have a steady, stable DC supply, as a variation might damage the components or introduce unwanted signals.
Providing a steady, stable DC supply from mains AC takes 4 steps. First, 240 volts AC is transformed down to the working voltage of, say, 9 volts. To change the AC into DC, we use semiconductor components called diodes. A diode is a one-way street for electrons. Semiconductors are materials like silicon, which have properties between those of a good insulator like glass and a good conductor like copper. By adding different impurities to pure silicon, we can make silicon with more electrons than usual, an N-type semiconductor, or fewer electrons than usual, a P-type semiconductor.
A diode is simply a junction between an N-type and a P-type semiconductor. Using a single diode, we can half-wave rectify an AC power supply. This means that we're only using half the AC wave. We can improve on this by using 4 diodes in this square arrangement called a bridge rectifier. This produces full-wave rectified DC, which uses the full AC wave. Full-wave rectification is the second stage in producing a steady, stable DC supply.
There are 3 other important types of diodes. The light-emitting diode gives off light when a current passes through it. The photodiode only allows a current to flow when light falls on it. The Zener diode allows no current to flow up to a certain voltage. It then starts conducting.
So we've seen how we reduce the incoming voltage from 240 volts off the mains down to a more manageable 9 volts. And we've also seen how the negative part of the wave can be flipped over to produce DC using a bridge rectifier. The last 2 stages in producing a steady, stable DC supply are called smoothing and stabilization. And it's those 2 sections that we'll be looking at today.
Unfortunately, the DC from a rectifier is a series of positive voltage pulses, a constant flow of bumps. Now, if you've ever ridden over bumps on a bicycle, you'll know that it isn't very nice. And what our electronic components want is a nice, smooth, steady supply. They want to ride their bicycle over a tarmac road, not over cobblestones. Take a robot arm, for example. It has to have a perfectly smooth power supply in order to produce a perfectly smooth movement. So the output of the rectifier must pass through a smoothing circuit. If we take the smoothing out of the power supply, our robot will suddenly develop a bad case of the shakes. So what we have to do is fill in the cobbles, smooth out the wrinkles. How do we do this? Well, you might have got a hint from last week's program.
Do you remember where high-frequency alternating current was used to melt steel? Last week, we saw how important diodes are in, first of all, converting the AC coming from the transformer into DC, and then converting that DC back into high-frequency AC. In the big green cabinet that does all that, there's another section that we didn't see last week. in this cabinet, these grey metal boxes smooth the rectified DC and provide a steady, smooth supply to the next set of diodes. They're called capacitors, and if you followed power base, then you'll already be familiar with what they can do. We also saw capacitors smoothing the power supply to the trucks, which carry around car bodies. Roger Long explains.
We take 35 volts AC through the external circuit breaker, through these wires to the internal circuit breaker. From that point on, we split the supply. One part goes to the motor control system. The other part we take through this 35 volt to 24 volt transformer, through another circuit breaker, to a bridge rectifier, through a smoothing capacitor, to the programmable controller, which is the brain of the truck.
So the smoothing we're looking for is achieved using capacitors. But how? Well, first of all, let's look back to power base and see exactly what a capacitor is.
A capacitor is just two plates of metal separated by an insulator. When a voltage is applied, electrons are pushed into one side of the capacitor and out of the other side. When one side is full and the other is empty, the capacitor is charged. If the voltage then changes, the electrons will float back round the circuit and even out the balance. With DC, a current flows while the capacitor is charging up, but is then blocked completely. With AC, the capacitor charges then discharges continuously, so there's very little resistance to the flow of electrons.
So a capacitor is an electron store. It has the ability to fill up with electrons when a voltage is being applied, then to put those electrons back into the circuit when the voltage goes down. And a flywheel does a similar sort of thing. This old sewing machine is operated by the treadle at the bottom. Now, if I was to operate the machine directly from the treadle, I would get very uneven stitches because I would first be pushing with my toes and then with my heels. So the inventors put in a flywheel, and that acts as an energy store and evens out my rough inputs of push. Now, a manual potter's wheel works on exactly the same principle. The rough, unsteady input of the occasional push by the potter's hand is stored up by the wheel and then let out again very evenly.
What our capacitor is doing is exactly the same. During the high part of the voltage pulse, the capacitor is having electrons forced into it. It is, in effect, storing them up. Then when the voltage drops off between the pulses, those electrons are released to fill in the gaps. So it's cutting off the peaks, storing them, and then later filling in the troughs with the electrons that have been stored. Now, let's have a look at that in action on the kit.
I've connected the power supply as far as the bridge rectifier, and you can see the sort of supply that's giving me on the oscilloscope. It's giving unsmoothed, rectified DC, which is a series of positive voltage pulses. But if I connect in a smoothing capacitor, like this one here, the output is smoothed and the troughs are now filled in by the peaks. Now, by putting a resistor across here, we limit the amount of charging current which is drawn by the capacitor. Then to complete the smoothing circuit, we add another capacitor on the other side of the resistor, which again reduces the ripple. Now, don't worry about exactly how this works. The important thing to remember is that this layout with two capacitors and one resistor is a common smoothing circuit, and it's called an RC filter, which stands for a resistor capacitor filter.
Let's see it at work. Certain pieces of equipment, computers, particularly those that operate in networks, checkout tills in supermarkets, collect a lot of information during a day, and then in the evening, all of that information is passed on to a central computer. If machines like this are working off the mains, and for some reason or another that mains is interrupted, all of that information will be lost, which could prove very expensive. So to avoid this happening, many computers are now powered through systems called uninterruptible power supplies. And we went to Siemens to see how a UPS is constructed.
The way an uninterruptible power supply works has quite a bit in common with the induction furnaces we saw in an earlier programme. Mains electricity comes into the UPS through the transformer and then passes on to a set of diodes, a bridge rectifier, to be converted into DC. These two capacitors are then used to smooth out the DC, which keeps a set of batteries charged up and also supplies a set of special switchable diodes which turn the supply back into AC. If the main supply fails, then the batteries step in and provide a DC input for the switchable diodes to turn into AC. In this way, the power supply to the computer isn't interrupted as long as there's electricity left in the batteries. Here, a fully constructed UPS is being tested to check that all stages of its power supply are performing the correct function. First of all, the computer is plotting the input of the bridge rectifier on the screen. As you can see, it's an AC waveform, as we would expect. Next, the computer plots the output of the rectifier before it's been smoothed. You can see that the output is a series of positive voltage pulses. And if the two traces are brought up on the screen together, you can see how the next part of the AC wave has been flipped up to produce a series of positive pulses. Finally, the computer plots the output of the rectifier after the capacitor smoothing has been added. A nice, smooth DC supply.
So those are the first three stages of our power supply: transformation, rectification and smoothing, giving us an almost ripple-free DC voltage, smooth and stable enough to be used on many basic circuits. But there are some circuits, such as microprocessors, where we need to add even more control. Fenella Hume is with us as usual. Why is this necessary, Fenella?
Well, some of the components inside microprocessors themselves are very, very sensitive, and so even the small bumps left by the RC filter are too much for those devices, so we need to smooth those out. Secondly, the power station itself doesn't give out 240 volts all the time. It's allowed to vary the output below that down to, say, 225 volts, possibly up to 255 volts. So what you get is a varying AC mains into your transformer, which gives you then varying DC on the power supply. That we have to take care of as well. The third reason, and this is quite clever, is that if you change the load on your circuit, for example, when you actually turn the volume control on the TV, for example, you're changing the resistance in the circuit. That is changing the load, and that also affects the voltage out of the power supply. So that too we need to take care of.
Thank you. So let's recap. We have to iron out the last few wrinkles. We have to take into account the variation in mains voltage, and we have to allow for any variations in the load on the power supply when part of the system is switched on.
Have you ever noticed that if you're having a shower upstairs and somebody downstairs turns on the hot tap, your shower suddenly goes cold? Well, the reason is that because of the diameter of the pipes, the boiler can only supply so much hot water at once. So there's a certain amount of hot water being taken through the system, and at the moment it's all going through the shower. Then someone elsewhere turns on the hot tap, and that increases the demand for the hot water from the boiler. If the total demand from your shower and from the hot tap is more than can go through the pipe leading out from the boiler, then the pressure at your shower will drop. Less hot water will get through, and so the shower suddenly goes cold. Well, things work in exactly the same way with electricity. And at the moment, the kit is wired up to provide a power supply to its built-in radio receiver and amplifier section, going first through the bridge rectifier and then through the RC filter. Now, by measuring the output voltage across the RC filter, you can see that it's about 10.9 volts. Now, by putting this 100 ohm resistor into the load sockets, I'm going to draw extra current from the power supply. And if I measure the output voltage from the power supply again, it's only 9.9 volts. So by adding the extra load, we've caused the output of the power supply to drop by 1 volt. And just like the hot water boiler, the power supply can only supply so much electricity at any one time. If I'm just running the radio, well, that's fine. But then if I increase the demand for electricity by adding the resistor here, the power supply can't cope with the demand and the pressure, the voltage, drops. So that's the problem. But how do we get around the problem?
Last week, you'll remember we introduced you to the Zener diode, and you'll remember that like a normal diode, the Zener lets current flow through it in one direction, but not in the other, unless, that is, the voltage goes above a certain value. So if a Zener is connected the opposite way round from a normal diode, then as long as the voltage is below its critical value, it will not let any current through. But as soon as the voltage rises above that value, it will let current through. And this critical voltage is known as the voltage rating. And Zeners are available in a wide range of voltage ratings from 2 volts upwards. What we've got here is a Zener diode, this little chap down here, connected to a variable DC supply. And you can see the voltage of that here. There's a second voltmeter in the experiment here, which is measuring the voltage across the Zener itself. And what I'm going to do is steadily increase the voltage from the power supply. I have a resistor up here in series with the Zener diode so that not too much current goes through it and destroys it. In a power supply, this resistance would already be present in the form of the resistance of the secondary winding of the transformer, the diodes in the rectifier, and the resistor in the RC filter. Right. Let's increase the voltage and watch the readings on these 2 meters. First, they go up together because the diode is stopping all the current and therefore taking the whole power supply voltage. But we'll reach a point, and there it is. You see, one of them has stopped going up. The voltage across the Zener stops increasing, and indeed I can go on increasing the voltage to the power supply for quite some time before it has any effect on the voltage across the Zener diode. Now what's happening is that the Zener has reached its breakdown voltage. It has started to pass a small current. As the voltage from the power supply continues to go up, the Zener passes a bigger and bigger current and is in effect sharing the total voltage between itself and the resistor. The result, as you see, is that the voltage across the Zener remains the same. So to produce a stabilized power supply, what we do is take the output of the power supply, not from the RC filter, but from across the Zener diode. Then, within certain limits, no matter how much we vary the load on the power supply, the output voltage will remain the same.
And I can show you that on the kit. This is the Zener diode, and I now have the kit connected up so that I'm taking the power supply from across the Zener. Now I'll first measure the voltage going into the amplifier without an extra load resistor as we did before, and you can see that it's about 9.5 volts. Now I'm going to put the extra load resistor in just the same way again as we did before, and take the output voltage again, and you can see that the voltage has remained exactly the same at 9.5. Now the power supply's output voltage was higher when the Zener diode wasn't connected, and that's because the Zener diode takes a relatively high but varying voltage and gives out a lower but very stable voltage. Now on your kit, the Zener takes an unstable voltage from the RC filter of around 10.9 volts, the voltage we measured before, and reduces it to a stable voltage of about 9.5 volts.
Well, let's develop this demonstration a little bit and see what happens when I start to load the power supply. With no load, you can see that the power supply output is 15 volts, whilst the voltage across the Zener is 9.5. Now, I'm going to start switching on bulbs to load the supply. With each extra bulb, you can see that the power supply is going down a little, but the voltage across the Zener, that is the voltage supplying the bulbs, remains constant. So, But that only happens as long as the power supply output is greater than the voltage rating of the Zener. And at this point, I've switched on 3 bulbs, and you can see that the voltages are almost the same. One more bulb, and the power supply dips below the Zener voltage rating, meaning that the output voltage of the system is no longer stabilized. Any more load, and all the bulbs lose power. So a Zener diode takes a relatively high unstable voltage and gives a lower but stable voltage. Zener diodes provide a cheap and simple method of stabilizing power supply voltages. But there is another way to do it, and that's to use an integrated circuit stabilizer called an IC stabilizer, sometimes known as a voltage regulator. These have all the features of a Zener diode, plus some internal circuitry which protects them against overloads and short circuits. So what would happen if I put a short circuit across the output of the Zener diode? Well, let me put on the safety glasses first, and we'll see what happens. Whew. So, shorting the Zener effectively destroys the power supply. But with a voltage regulator, that wouldn't have happened, because the internal circuitry of these components would have protected against the short. Now really, all you need to know about voltage regulators is that they are very clever little black boxes. There are 2 types: fixed voltage regulators, this is one, it has 3 connections, and variable voltage regulators, which have 4. And as you might have guessed, the difference is with the variable voltage regulator, you can use the 4th connection to vary the output voltage. Incidentally, the voltage regulator on your kit is variable. Fenella, I wouldn't blame anybody for finding that last bit just a little complicated. Is there another way of looking at this?
Well, if you think about it like buying a car, you go in to the showroom, they give you a car which you fill with petrol, you press the accelerator, and off you drive. All we're saying here is accept that these little black boxes are just as simple. Obviously not inside, but to use them, all you need to do with the 3-legged one is connect it to a power supply, and you'll get a fixed voltage out. The 4-legged one, that 4th leg for that extra control, is a variable one. It really is as simple as that.
Thank you.
But as that's all we have time for this week, you'll have to follow that up with your own kit through the Open College course on Basic Electronics. And for details of that course, please write to Circuit Training, the Open College, P.O. Box 35, Abingdon OX14 3BR. The training package, like these programmes, starts from the assumption that we know nothing more than the very basics of electricity and takes us through to a simple understanding of this fascinating subject.
So join us again next time on Circuit Training, and we'll continue our television background to basic electronics. But let's leave you with a final reminder of what we've covered today.
The output of a full-wave rectifier is not smooth enough to be used by most types of electronic circuits because its variations can cause signal distortion. These variations can be removed by using a smoothing circuit, such as a capacitor or an RC filter. The capacitor smooths the voltage by storing electrons during the voltage peaks and putting them back into the circuit during voltage troughs. Adding an extra load to a power supply will cause a drop in its output voltage. To prevent this, the voltage can be stabilized by using either a Zener diode or an IC stabilizer. A Zener diode is put in the final stage of a power supply and provided with a voltage of a few volts higher than its voltage rating. The load is then connected across the Zener diode and is provided with a stable DC supply.
And that's it. Good luck with your own work, and until next time on Circuit Training, from us all, goodbye.
Time now for a quick burst of circuit training.
Hello, welcome to the fourth in our series of circuit training. In today's program, we meet transistors, the electronic switches which make so much of our modern world a reality. And we see how almost 90,000 transistors operate this tiny television screen.
And also how millions can be fitted onto this tiny piece of silicon to form the famous silicon chip. But first, let's see what we've learned so far. In the first program, we learned that electronics is concerned with handling tiny voltages and currents called signals. Because signals are so small, we need to use amplifiers to magnify them into useful working voltages. Also, it's very important for electronic equipment to have a steady, stable DC supply, as a variation might damage the components or introduce unwanted signals.
Providing a steady, stable DC supply from mains AC takes 4 steps. First, 240 volts AC is transformed down to the working voltage of, say, 9 volts. To change the AC into DC, we use semiconductor components called diodes. A diode is a one-way street for electrons. Semiconductors are materials like silicon, which have properties between those of a good insulator like glass and a good conductor like copper. By adding different impurities to pure silicon, we can make silicon with more electrons than usual, an N-type semiconductor, or fewer electrons than usual, a P-type semiconductor.
A diode is simply a junction between an N-type and a P-type semiconductor. Using a single diode, we can half-wave rectify an AC power supply. This means that we're only using half the AC wave. We can improve on this by using 4 diodes in this square arrangement called a bridge rectifier. This produces full-wave rectified DC, which uses the full AC wave. Full-wave rectification is the second stage in producing a steady, stable DC supply.
There are 3 other important types of diodes. The light-emitting diode gives off light when a current passes through it. The photodiode only allows a current to flow when light falls on it. The Zener diode allows no current to flow up to a certain voltage. It then starts conducting.
The output of a full-wave rectifier is not smooth enough to be used by most types of electronic circuits because its variations can cause signal distortion. These variations can be removed by using a smoothing circuit, such as a capacitor or an RC filter. The capacitor smooths the voltage by storing electrons during the voltage peaks and putting them back into the circuit during voltage troughs. Adding an extra load to a power supply will cause a drop in its output voltage. To prevent this, the voltage can be stabilized by using either a Zener diode or an IC stabilizer. A Zener diode is put in the final stage of a power supply and provided with a voltage of a few volts higher than its voltage rating. The load is then connected across the Zener diode and is provided with a stable DC supply.
So now we have our perfect supply, DC, smooth and stable, and we can start to supply a whole range of electronic circuits. The component we're going to talk about today and next week is the most basic building block of any circuit, the transistor. The transistor has made a major impact on all walks of life since its invention in 1947, because it is the most basic component from which all computers are made. But in itself, a transistor is incredibly simple. It's just a switch. It either allows a current through, or it doesn't.
A bit like this turnstile. Now imagine the scene at a football match with the pressure, the voltage building up as fans want to get through. And if there were a stream of fans, as there would be a stream of electrons, they would only get through while I was pressing the button. As soon as my finger comes off, the stream would stop. Now, a transistor has 3 legs. That's 3 electrical connections, or electrodes. One of them lets the current in. That's the flow of fans in. Another lets the current out again. And the third is the button, which decides whether or not there's to be a flow at all.
If you watched our power-based programs, you'll be familiar with this component. It's a relay. When it's switched on, current is supplied to this coil which magnetizes the electromagnet, pulling in the metal here, closing the contacts round here. Watch. Open, closed, open, closed, open, closed. Now this allows a much larger current to flow between the input and the output here. With the relay connected up with the circuit that we've got here, the output from the coil is the same as the output from the main switch. It's just a return line to the battery. So what we have is a very large current flowing through the bulb and then through the switch in the relay, controlled by a very small current coming through this resistor, this switch, to the coil in the relay. Now, you may be wondering what the letters B, C, and E stand for on the board. Well, with a relay connected up in this way, we are actually mimicking the actions of a transistor. And by moving onto this board, I can show you what I mean. We've got exactly the same layout of battery, resistor, switch, and bulb, only instead of the relay, we have a transistor. The B, C, and E are the names of the electrodes of the transistor. The small controlling current comes into B, the base. The larger current comes into the transistor through the collector, C, and it leaves the transistor through the emitter, E. The base current also comes out of the transistor through the emitter. So a transistor is as simple as that. It is an electronic switch. 3 connections: in, the collector, out, the emitter, and on-off, the controller, the base. Now, how can you remember the names of those electrodes? Well, the inventors of the transistor were given a Nobel Prize. They were American. But had they been British, perhaps their invention, with its collector, base, and emitter, would have gained them a CBE. Anyway, let's see the transistor in action on the kit.
Now, the kit is set up to demonstrate the transistor acting as a switch. And they've also put a light-emitting diode, an LED, here, and that's connected up to the transistor. Now, starting with this variable resistor at its maximum resistance, as I gradually turn it, I'm letting a small signal current go into the base of the transistor. Now remember, this is the current which controls whether the transistor is on or off. Now, when the current is large enough, the transistor suddenly switches on, and as you can see, the LED comes on. But if I turn the resistor back, I cut off the small signal current to the transistor and so switch off the LED. So that's what a transistor does. But how does it do it? Well, there are many different types of transistor and they work in various ways, but they all do exactly the same thing. They all use a very small signal current to control the through current. Now, here's one way of thinking about how a transistor works.
This is a transistor. The base is at the top, the collector on the left, and the emitter on the right. In a transistor, a current coming in through the base is needed to let the much larger current coming from the collector get through to the emitter. With the base current on, the transistor is on. If there's no base current, no current flows between the collector and the emitter, and the transistor is off. Jumping from one state to another is using the transistor as a switch.
Fenella Hume is with us as usual. Fenella, we've established that the transistor is nothing more than a simple switch. What are the advantages it offers over ordinary switches and relays?
Well, the first you can imagine is it has no moving parts. That means it won't wear out. It's much more reliable than a switch that is mechanically moving. The second thing is the size. It's so small that it can actually, hundreds of these things can be put into a small area, which means you can get lots of them in one circuit. The third thing is the speed. They work very, very fast. That means you can switch them on and off maybe 1,000 times a second. Our modern computers are so powerful because you have things that switch very fast and are very small and don't often break down.
Thank you. So, a transistor is a very small, very fast switch. And you can see how small a transistor can be if I tell you that there are almost 90,000 transistors actually embedded in the screen of this tiny television. Research expert Bernard Green explains how this screen works.
We have here a model of a screen which has only 64 by 64, 4096 pixels. If I switch it on and off, you see it responds to the voltage. There are 4096 tiny shutters, in fact, which are used to make up the picture. And over each of these shutters there is placed a tiny patch of colour, either red, green or blue. All colour pictures on displays are made up in this way. If you look at your television set here, you will see that the whole picture is made up of tiny dots of red, green and blue colour. By applying voltages in that direction and simultaneously in this direction, we can address any single pixel within that area. And the television picture is sequentially built up line by line in scrolling down the screen, and this happens that there is a new picture built up at every 25th of a second. Each pixel, however, doesn't know whether it's on or off, and so there has to be some means of building in a memory into the pixel. And to do this, a tiny transistor is incorporated in each of the pixels. Using our electron microscope, we have produced some electron micrographs of a single pixel, which you can see is this square area here. You can see the conductors which supply the voltages to that pixel around the outside of it. And in the corner here, you can see the transistor. We have here another picture at an even higher magnification, and you can see the transistor very much enlarged here. If we look at this magnified picture of a liquid crystal screen on the wall here, you can see the green, red and blue pixels. You can see the size of the pixels, which are 150 micrometers. And in the corner of each pixel, you can see a tiny thin film transistor. And it's these transistors which control the state of the pixel during every part of the process. Now, to give you some idea of just how many pixels are required and the size of the pixels, here is a 3-inch diagonal screen, and it has over 88,000 transistors in it.
So in this screen, all those 88,000 transistors are individually acting as switches, each one controlling an area of red, green or blue light. But these transistors are acting individually, and the real power of a transistor comes out when it acts together with others of its ilk. Why is that? What's so special about an electronic switch? And why did the invention of the transistor have such a great effect on the world?
The important property of the transistor is that, like any switch, it can flip from being completely on to completely off. And it's this fact that lies at the very heart of computers. You may well have this type of arrangement at home. 2 switches, perhaps one at the bottom of the stairs and one at the top, both controlling a light. Now, either switch will turn the light on or off. Now, if I call the up position of the switches 0 and the down position 1, I can write down when the light is on and when it's off. With both switches at 0, 0 down there, 0 up at the top, the light is on. Also, if both switches are at 1, the light is also on. But if one switch is at 1 and the other at 0, the light is off, no matter which way round those switches are. In fact, we can say that the light is on if and only if both switches are in exactly the same position. That is, A equals B. Now, this type of condition, doing something if and only if 2 other things are equal, is exactly the sort of thing that computers do. And this particular circuit is very useful for lighting your way to bed, but certainly it isn't going to help you calculate your shopping bill. However, if we put enough switches together in the right combinations, we could make a calculator. A few thousand for a simple calculator like this, a few million for a small computer. Computers are now part of everyday life. Indeed, at every company we've visited, there has been some sort of computer. Here, controlling robots at Austin Rover in Cowley, and here, monitoring light bulbs at Thorn Lighting. Almost every office has at least a word processor. And how do many people get their cash these days? By computer.
Yet the first machine that could realistically be called a computer was invented way back in the 1820s by an English scientist, Charles Babbage. Of course, this was well before the days of the transistor, so his analytical engine was entirely mechanical, containing around 50,000 moving parts. It was in 1936 that Alan Turing, a young mathematician, realized that by breaking problems down into a set sequence of steps, a simple machine, indeed the future computer, could solve them. 2 years later, Claude Shannon, an American, showed that a device of just two positions, on and off, could be used to make such a machine. A year later, with the outbreak of war, the development of the computer suddenly accelerated. Here in Britain, at Bletchley Park, over 1,500 glass valves, the forerunner of the transistor, were put together to form a machine called the Colossus for the specific purpose of decoding intercepted German radio signals. The electronic computer had been born. The first transistor worked at Bell Laboratories on the 23rd of December 1947. 9 years later, the inventors John Bardeen, Walter Brattain, William Shockley were awarded a Nobel Prize for what was described as the discovery of the century. True, the original transistor was fairly bulky, but because it relies on semiconductor properties, a transistor can be made smaller and smaller, and yet still be able to perform the same switching function. Smaller transistors not only use less current, but also operate faster because the electrons carrying the current have a shorter distance to travel. In 1954, Texas Instruments produced and sold the first transistors. At £20 each, they were fairly expensive. But prices fell rapidly, and by 1965, transistors were only 20 pence each, 100 times cheaper. Today, an individual transistor, like the ones on the kit, cost only a few pence. But also, costing only a few pence, is the silicon chip, the integrated circuit. It's called an integrated circuit because many hundreds of transistors have all been integrated into one circuit contained within a little black plastic package. So, if you want to buy transistors already wired up into circuits, they now cost a tiny fraction of a penny.
The most complex integrated circuits now contain upwards of 1 million transistors. And obviously the design of this type of chip is incredibly demanding. We went to Thorn EMI's Central Research Laboratories to see how John Strange uses one computer to help him design another.
Here at the CAD VLSI department, what we are concerned with is the computer-aided design of very large-scale integrated circuits. What we do to design a chip is to put together thousands of transistors, all acting as switches, in such a way that the desired function is implemented. Now, many years ago, this was simply done using pencil and paper. But today, the problem is far more complex, and what we've got to use instead is computers. The computer doesn't actually design the chip itself, they're not quite that clever yet. But instead, what we do is program the computer using the rules of chip design, and when we break these rules, the computer will tell us, and we can make the corrections. Another thing the computer does is to act as memory to store the chip design. Now, I can bring up from memory a single transistor onto the screen, like this. And here, I can show you the collector of the transistor. Here, in green, we have the base, and the final terminal here is the emitter. Now, using the graphics to design, I can simply take the transistor and copy it to give myself two transistors. Now, to make a circuit, all I need to simply do is connect these transistors together. In this case, connecting the base of this transistor here to the base of this transistor here. Now here are two more transistors in a circuit. And if I zoom out, you can see how we connect these transistors together. Here we have about 6 transistors, and now 100. I can't really show you any more because of the resolution of the screen. So instead, what we have to do is get a plot. This chip here contains around 100,000 transistors, all acting like switches. And when it's manufactured, it'll only be this large, about 8 millimeters square.
Fenella, 100,000 transistors on this tiny sliver of silicon. Is there any limit to how compact these circuits are going to become?
Well, if you want to answer a question like that, maybe you could look at the past a little bit to see if that helps. There was a chap back in 1964, I think his name was Moore, and he actually made a law that every year the number of transistors that could go on a chip would be doubled. And up to about 1980 and a little bit beyond, he was about right. But things have started slowing up now because we've reached the limit with silicon. We can't pack any more onto the material silicon. So what we need now is a new material so that we can use that technology with a new material and advance again from the beginning at the same rate.
What are the sort of materials then researchers are now looking at?
They're looking at things like optical transistors, which are faster because they work with light instead of electrons, and things called superconductors, which are just very, very fast and very small compared to a silicon transistor.
So how small are things going to get?
Well, if you can imagine, we're talking at the moment about hundreds of thousands of transistors on a chip. What the superconductors will mean is hundreds of thousands of computers on each chip.
And what's the benefit of that?
Well, it means computers are going to turn up in everything a lot more because they'll be so much more powerful.
And in terms of employment and job opportunities, how important is that going to be?
Well, if there are more computers around, the more you know about them, the better chance you have of getting a job.
Fenella Hume, thank you very much.
Well, with that vision of the future, I'm afraid we must leave. The most important thing to take out of this particular programme is that the transistor is an electronic switch. And remember that you can follow all of this out at your own pace through the Open College course on Basic Electronics. And for details of that course, please write to Circuit Training, the Open College, P.O. Box 35, Abingdon OX14 3BR. The training package, like these programmes, starts from the assumption that we know only the basics of electricity and shows us that by understanding the building blocks of electronic circuits, we can understand the circuits themselves.
Join us for our final programme next week and we'll round off this television background to basic electronics. But let's leave you with a reminder of what we've covered today. A transistor is a very small, very reliable, very fast electronic switch.
In a transistor, a current coming in through the base is needed to let the much larger current coming from the collector get through to the emitter. With the base current on, the transistor is on. If there's no base current, no current flows between the collector and the emitter, and the transistor is off. Jumping from one state to another is using the transistor as a switch.
Transistors, acting as switches, are the basis of all modern computers. Today, hundreds of thousands of transistors can be fitted onto one tiny piece of silicon.
Well, that's it. Good luck with your own work, and until next time on Circuit Training, from all of us here, bye for now.
Goodbye.
Life of the transistor.
Hello, welcome to the last programme in our series Circuit Training. In today's program, we're going to be looking again at the electronic switches we introduced you to last week, transistors, and we'll be seeing what happens when they're neither fully on nor fully off.
We'll see how transistors can be used to magnify the tiny signals produced not only by the radio circuit in the kit, but also by many other electronic circuits.
And we'll see how the transistor as an amplifier fits together with the computer and a steady, stable power supply to fit windscreens at Austin Rover's Cowley plant.
But first, let's have a look at what we discovered about the transistor last week.
A transistor is a very small, very reliable, very fast electronic switch.
In a transistor, a current coming in through the base is needed to let the much larger current coming from the collector get through to the emitter. With the base current on, the transistor is on. If there's no base current, no current flows between the collector and the emitter, and the transistor is off. Jumping from one state to another is using the transistor as a switch.
Transistors, acting as switches, are the basis of all modern computers. Today, hundreds of thousands of transistors can be fitted onto one tiny piece of silicon. So, like a switch or a relay, a transistor can be switched on or off, and we said that the advantages of the transistor are that it's reliable, small, and fast. But Fenella, there are other things that the transistor can do over and above the switch and the relay.
That's right. What you can do is get a transistor to switch either a little current or a lot of current. So if you imagine having a small current in the base, then you get a relatively small current at the emitter. If you increase that current just a little bit, then you can get a very large current at the emitter.
And can one vary this continuously?
Yes, you can, and that's exactly what we do. We take one of these signals we called a control signal and put it into the base of the transistor, and it's varying just a little bit. And what we get at the emitter of the transistor at the output is a very large variation in current.
Let's look at the practical application of that then. What's the benefit?
Well, small in, big out, it must be amplifying it. And this is what we were talking about, saying that we needed amplification. We need to take a small signal and make it into a big one.
Fenella, thanks. So it's the transistor's use as a signal amplifier that we're going to look at in this program.
Last week I showed you how the transistor could be used on the kit to switch on and off a light emitting diode by adjusting the variable resistor. Now this variable resistor is actually the volume control that you would find on a radio. But we'll remake the circuit, take the LED out, put a resistor in across that link, wire in there, and connect this circuit up to the radio receiver. Now, the two transistors, one here and one here, aren't being used as switches, but as amplifiers. And now, if I adjust the volume control, the variable resistor, you can hear that the volume of the radio goes up and down. If you've been watching circuit training, then you'll be familiar with this piece of equipment. It's an oscilloscope, and there are two traces on the screen. This one at the top is the output of the radio receiver. That's the signals that the radio gets from the aerial. And this one at the bottom is the output of the transistor amplifier. Now, with the volume control right down, as it is now, you can see that there's an output from the radio receiver, but nothing is coming through on the speaker and nothing is coming out of the transistor amplifier. Now, if I turn the volume up, you can see that a signal just the same as the output of the radio is starting to appear on the second trace. And as I turn the volume up, the signal gets larger and larger as the sound coming out of the speakers gets louder. Now, the transistor amplifier is working to magnify or amplify the signal it's getting from the radio receiver. And if I turn the volume control up and down, you can see that the size of the electrical output of the amplifier is going up and down as well.
So how is all this working? Well, in a minute we'll go through once again the workings of a transistor with the help of our electron. But first remember the three connections of a transistor. They're called the collector, through which current comes into the transistor, the base, which decides how much of that current goes any further, and the emitter, which takes the current back out of the transistor. And to remember the three, collector, base, emitter, think of CBE.
In a transistor, a current coming in through the base is needed to let the much larger current coming from the collector get through to the emitter. With the base current fully on, the transistor is fully on. If there's no base current, no current flows between the collector and the emitter, and the transistor is off. Between these two states, the collector current is proportional to the base current, only much bigger. The transistor is acting as an amplifier.
So the transistor is neither on nor off, it's somewhere in between. And in this region, a small increase in the base current produces a large increase in the emitter current. It's a little bit like a bicycle. If I push the pedal round one turn, the back wheel actually goes round 3 turns. My input is amplified, magnified 3 times from 1 turn to 3. Now, whether I speed up or I slow down makes no difference to that 3 times magnification. It remains the same. This is a somewhat unusual bike because it doesn't freewheel. As soon as my input stops, the wheel also stops. And we chose this design because it behaves exactly like a transistor amplifier. If you cut off the input at the base, then the output of the transistor is also cut off.
So how is this amplification, this increase of the input signal used in practice? Well, here is a transistor with an ammeter measuring the current which is going into the base and another ammeter measuring the current which is being allowed to pass through the transistor. Now, as I increase the current which is going into the base, you can see that the through current also increases. But notice the different scales of the 2 meters. When there's a current of 10 milliamps coming into the base, there's a current of 0.4 amps, that's 400 milliamps, coming through the transistor. That's to say 10 milliamps become 400 milliamps, an amplification of 40 times. In fact, the correct name for this is gain. The gain of this transistor is 40. Now, you may remember from the first programme in the series that Michael listened to the sound produced by a stylus as it travels over the grooves of a record. Now, if you listen very closely, you can hear tinny little sounds coming out of the stylus. In fact, it's almost inaudible. So if the output signal from the stylus is magnified many times, we can hear it through the speakers. So, say we need to amplify it thousands of times. That magnification or amplification is exactly what our transistors can do for us. In practice, this is achieved not with one transistor, but with several. Say, for example, we needed a gain of 1,000. 3 transistors, each with a gain of 10, will be able to cope. The first transistor increases the signal 10 times. The second transistor takes this increased output and increases it again by 10, giving a total increase of 10 times 10, which is 100. The third transistor then increases that 10 times more, which gives a total increase of 10 times 10 times 10, which of course is 1,000. But audio signals aren't the only things that are amplified by transistors. Computers, for example, produce tiny control signals to control servo motors, which in their turn control the position of a robot arm. But the output signals from the computer aren't big enough to directly control the motor. The signals have to be amplified.
What you can see here is a typical industrial robot control system. This control panel is linked to a computer which works out which way the various motors which will eventually control a robot arm have to turn in order to make the arm move in a particular way. The operator puts in instructions identifying the movements required. The computer, which as you remember is just a large number of transistors acting as switches, then calculates the signals it needs to send to the motors. These signals are then amplified by this transistor amplifier, and the motors turn accordingly.
there are two more things we need to know about transistor amplifiers before we see how they fit in with the various other ideas we've covered in this series. Let's have another look at the setup I was using a moment ago. As you remember, when I increased the base current, the current being allowed through the transistor also increased. But what happens if the input to the base is alternating? Well, the transistor only works one way. So if we try and push a current in the opposite direction, that's out of the base, nothing will happen. Now, if we're dealing with input signals which are always positive, obviously this isn't going to be a problem. But that's quite unusual. More often, the input signals will vary. For example, our computer might want to turn a motor first in one direction and then in the opposite direction a few moments later. So what we want is an even amplification of the input signal. But because a transistor can't amplify negative input signals, we would lose that part of the signal in the output. So how do we get around the problem? Well, basically, we bump up everything coming into the base by a fixed number of milliamps. And this is called biasing the transistor. If we bias the transistor by, say, 5 milliamps, then when there's no input signal at all, the base current is still 5 milliamps, which is, of course, allowing through a certain emitter current. Then an input signal arrives of, say, plus 2 milliamps. Now, this increases the base current to 7 milliamps, and the emitter current rises appropriately. Then, a little later, an input of minus 2 milliamps might arrive. This time, the base current changes to 3 milliamps. That's 5 minus 2. And this, of course, still produces an emitter current, although it's much lower. So that's how we handle negative inputs. We use biasing.
But if the biasing is set inaccurately, this can lead to all sorts of problems. Listen. Distortion. Distortion happens when the bias level is wrong. The input is forcing the transistors in the circuit to operate outside the limits of their capability. Now, this can happen either because the bias was set incorrectly in the first place, or because the power supply supplying that voltage is varying too much. It's not a steady, stable power supply. Perhaps the batteries are running down. What's happening is that the input current is not being smoothly amplified. The result, as you can hear, is fairly unpleasant. A steady, stable power supply is vital. We went to Austin Rover to see how power supplies, transistors acting as switches, and transistors acting as amplifiers are used to put windscreens in exactly the right place.
This part of Austin Rover's Cowley plant is entirely automated using computer-controlled robots to fit front and rear screens. When the car comes to rest, lasers measure the exact position of the window hole. That information then goes to the computer, which works out exactly where to fit the glass. The lasers, those red spots of light, check the positions once again. Then the computer calculates the exact movements needed to put the glass in the right place. The position of the glass is controlled by joints of the robot's arm, which are in turn controlled by these motors. So to get the glass put exactly in the hole, the computer has to tell each motor to move in a particular way. In the robot control box, we can see most of the concepts we've covered throughout the series. The power comes in through the main isolating switch and is transformed down to a suitable working voltage. It then goes through a 4-diode bridge rectifier to be turned into unsmooth DC. Capacitors are used to smooth this to provide a steady DC power supply for the computer and the amplifiers. The computer is made up of thousands of transistors all acting as switches. These transistors can work out exactly how each motor needs to move. Once the calculations are complete, it sends the signals up to the transistor amplifier circuits. They amplify the few millivolts that the computer produces into the several volts needed to make the motors move in a way which places the glass into the car windows.
And of course, in that report, you saw a lot of what we've covered in this series coming together. In a moment, we'll be conducting a whistle-stop tour of the whole series. But before that, let's have a word with Fenella. Can we clarify how important transistor amplifiers are, because I'm sure there are one or two people who still think of the black box in the music center whenever anybody says transistor amplifier.
They do. They're very familiar with that because of the first transistor radio. But now we use transistors just about everywhere to take those little control signals we're talking about and make them into big current that we can do work with. So apart from the music, you've also got things like a microwave oven. That's the thing you want to do the work of cooking your food, but all you do is press the button. A little thing happens there and you get a big amount of food cooked. In offices, they're used all the time in calculators, typewriters, computers, all that sort of thing. And as we've seen on films, in heavy industry, smelting metal, moving robots, all those sort of things you need to have transistors in as a basic amplifier.
Now, right at the start of all this, you said we're going to make it nice and simple by thinking of these circuits as black boxes. And yet here we are, we've devoted a large amount of time to studying one component, the transistor. Why is it so fundamentally important?
Well, it is the first building block that we use to make up all these other complex circuits. It is in itself a black box because, having explained it, we can now forget about it and say just what it does. It's an amplifier. We can then put it together with lots of other black boxes and make another big box that has a function. That's what we do all the time.
When we were talking about electricity, we made it clear that electricity is dangerous. Now, with electronics, we appear to be dealing with low voltages, low currents. Does one have to take care with electronics as well?
Yes, you still always have to have this very healthy respect for any electricity. You may be working with small voltages and currents, but they're supplied in the first place from mains. So from that point of view, you must always be careful. The sort of thing that I do maybe is wear rubber-soled shoes, because that'll stop the electricity having a path through your body to the ground. Another useful tip is to work with one hand in your back pocket, so that if the other hand accidentally touches electricity, it won't have a path straight across your heart, which is very dangerous. A third thing is, don't take it for granted that even though you've switched something off, it's safe. Remember our television with the capacitors in. If you touch those capacitors, even with the power off, their stored electricity could still hurt you. And another very simple thing is jewellery. Don't wear jewellery because it conducts, and it'll conduct straight to you.
It is an important energy source, though, isn't it?
Oh, it is. Very valuable and very powerful, but do respect it.
Fenella, thank you very much, and indeed thank you for all the help that you've given us throughout this series. Because we're now almost at the end of circuit training. But before we say our goodbyes, how about a whirlwind tour of the last 5 programs?
Electronics is to do with the handling of very small voltages and currents called signals. The signals used by electronic equipment need to be boosted to provide a useful output. To do this, we use amplifier circuits. Most electronic circuits run on low voltage DC power, and the voltage must be kept smooth and stable to prevent distortion of the signal or damage to the components. This voltage can be supplied by batteries or by the equipment's power supply.
A power supply comprises 4 basic sections. The transformer, which changes mains voltage AC to low voltage AC. The rectifier, which changes the AC to DC. The smoother, which evens out the bumps. And the stabilizer, which further refines the supply.
The input voltage of a transformer is applied to the primary coil, and the output voltage is produced by the secondary coil. The input and output voltages are in the same proportion as the number of turns on the primary and secondary coils. If the secondary has more turns than the primary, then the output voltage will be higher than the input voltage. If the secondary has fewer turns than the primary, then the output voltage will be lower than the input voltage.
Semiconductors are materials like silicon which have characteristics halfway between those of a good insulator and a good conductor. By introducing certain impurities, we can either give the semiconductor more electrons than usual, creating an N-type semiconductor, or fewer than usual, a P-type semiconductor. By putting together these 2 types of semiconductor, we can make a diode, which only lets electricity flow in one direction. As well as signal, low power, and power diodes, There are light-emitting diodes, which light up when current flows through them, photodiodes, which only let a current pass when light shines on them, and xenodiodes, which are used to control voltages. We can use a single diode to change AC into DC, but it only lets positive half cycles of the AC wave pass through it, and so it's called a half-wave rectifier. It's better to use 4 diodes connected up to form a bridge rectifier. In this way, we can use both the positive and the negative half cycles of the AC wave.
The output of a full-wave rectifier is not smooth enough to be used by most types of electronic circuits because its variations can cause signal distortion. These variations can be removed by using a smoothing circuit, such as a capacitor or an RC filter. The capacitor smooths the voltage by storing electrons during the voltage peaks and putting them back into the circuit during voltage troughs. Adding an extra load to a power supply will cause a drop in its output voltage. To prevent this, the voltage can be stabilized by using either a xenodiode or an IC stabilizer. A xenodiode is put in the final stage of a power supply and provided with a voltage of a few volts higher than its voltage rating. The load is then connected across the xenodiode and is provided with a stable DC supply.
A transistor is a very small, very reliable, very fast electronic switch.
In a transistor, a current coming in through the base is needed to let the much larger current coming from the collector get through to the emitter. With the base current on, the transistor is on. If there's no base current, no current flows between the collector and the emitter, and the transistor is off. Jumping from one state to another is using the transistor as a switch.
Transistors, acting as switches, are the basis of all modern computers. Today, hundreds of thousands of transistors can be fitted onto one tiny piece of silicon.
Transistors can also be used in between being fully on and fully off, and this is using the transistor as an amplifier. Amplification means using a small signal, such as a small current, to produce a larger one. When a transistor is used as an amplifier, a small signal current is fed into its base, and this allows another current, the same as the first one but larger, to flow through the transistor. The gain of a transistor, or amplifier, is the number of times the output signal is greater than the input signal.
So there you are, 5 programs in as many minutes, and you can follow up this program and indeed the whole series at your own pace with the Open College course on basic electronics. And for details of that, write to Circuit Training, the Open College, P.O. Box 35, Abingdon, OX14 3BR.
The training package, like these programs, starts from the assumption that we know only the very basics of electricity and shows us that by understanding the building blocks of electronic circuits, we can eventually understand the circuits themselves.
And that's it. If you've been following the series together with the training package, then I hope you found it helpful. If you've just been watching out of interest, well, perhaps you should think about joining up and following the Open College course. But for now, from Fenella, Carol and myself, goodbye. And let's leave you by hearing what people involved in industry think about the study of electronics.
It's certainly very rewarding to study electronics at whatever level.
Electronics is a thing of the future, isn't it?
Once you've done training, you feel more confident, you know what you're doing, and it's what you need.
If you stick your head in the sand and sort of say, no, I'll do it my way, you'll just get left behind. You've got to go with the future.